So in the area of batteries, I want to mention one of the recent development we're very excited about is, for lithium-ion batteries, we always want to push for more energy, right? So this is really driven by the electrification of light-duty vehicles, right? For electric vehicles, we want to essentially bring the cost down. We want to drive longer. Right? Essentially, that can be enabled or facilitated by the higher gravimetric energy density or higher volumetric energy density of lithium-ion. So folks are looking at putting more and more nickel into the positive electrode, right? To essentially replace cobalt, right? So to lower the cost, right? As well as increase its energy density, right? So with high nickel based positive electrode, one of the downside or disadvantage is that we were not able to cycle the batteries as long, right? We see more enhanced degradation with the conventional carbonate-based electrolyte. And so together with some colleagues, Jeremiah Johnson, as well as Julie, that we have been able to develop electrolyte or new electrolyte solutions that replace the carbonated electrolyte that can essentially stabilize the electrolyte and the electrode interface, enable the use of a nickel-rich based positive electrode. In addition, this electrolyte also enable the reversible or stable lithium electrolyte surface interfaces, so potentially allow us to replace graphite with lithium. It really, I think, is one potentially solution to significantly increase the lithium-ion batteries. And I think this potentially also offers opportunities to reflect, can the liquid electrolyte also stabilize metallic lithium, right? So there's a lot of work in the community utilizing solid-state batteries or solid-state electrolyte to stable lithium, right? So a lot of investment, a lot of research going into that particular area, and again driven by the transportation or light-duty vehicle, right, to electrify that sector, right? But with a solid-state electrolyte, we have the challenges of how do we manufacturing these solid-state batteries, and how do we connect these manufacturing of solid-state batteries and build upon existing lithium-ion battery manufacturing facility, right? And if we can actually develop and enable a liquid electrolyte lithium metal technologies, which our recent work shows that possibility, then we can essentially have a drop-in technology and leveraging the existing lithium-ion battery manufacturing infrastructure and to make lithium to be adapted to manufacturing lithium metal. Right? So I'm excited about this invention or this technology solution because it offers the possibility of liquid electrolyte can rival essentially with the promise of lithium metal batteries enabled by solid-state electrolyte. So we built a framework of controlling electronic structure of oxides to control essentially the catalytic activity, particularly the surface oxygen catalytic activity, how they will interact with molecules. It just turned out the more nickel we have or the more lithium we remove from the material, the oxygen on the surface become more and more reactive towards the carbonate electrolyte. Essentially, the carbonate electrolyte will absorb onto the surface and become dehydrogenated, right? So essentially, they come to the surface and dissociate and strip essentially the hydrogen from carbonate electrolyte and to generate protic species. And these protic species are typically we want to avoid in lithium-ion batteries, right? Because the protic species react with the salt and they essentially degrade the electrolyte. We lose essentially ion conductivity through the process. So with this understanding, and together with Jeremiah, we designed a new electrolyte based on sulfur amide, where essentially the solvent are free of these hydrogens that might be subject to dehydrogenation. And then we develop this new electrolyte, and that is essentially stable against nickel-rich or positive electrode. Right? So I just want to sort of highlight the importance of this fundamental research of looking at electrolyte interface, understand how they react mechanistically if you vary the electrolyte, right, as well as vary the surface chemistry or the electronic structure to vary the interactions is really key to potentially developing or in seeding future innovations. And I want to highlight this fundamental research and come from a long-term and a substantial funding with our engagement with BMW, which make it possible.